Good evening, everyone. So, hope you are doing very well. As you all know, that today we are going to see the theory of our third chapter, which is chemical kinetics, right? So, let's start with our topic, which is NCRT chapter 3, chemical kinetics, theory part third, part 3. Disclaimer: the images, text, and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of original creators and owners. If you are the owner and have any concern or issues, please contact us at sathi@iitk.ac.in and we shall remove the content immediately. Please note that the parts of the content may have been generated using the generative AI, which is experimental. So let's start or let's begin with our first thing, which is objective. What is today's objective? So after attending the today lecture or this lecture, you will be able to first of all distinguish between the elementary and the complex reactions. Okay, so how the elementary and the complex reactions are different from each other. You will be able to distinguish between them. You can differentiate between the molecularity and the order of a reaction, and you can also able to define the rate constant for a particular reaction. Now let's see that which are the topics which we will going to cover today in this lecture as per the NCRT. The first is the section or subsection 3.2.3, which we will going to cover, which is order of a reaction, in which we will talk about the unit of rate constant, and then we will see the next subsection, which is marked as 3.2.4, that is molecularity of a reaction, and it is elementary reaction. Okay, under this we will study about the elementary reaction, complex reaction, determining the order of the reaction. So we also learn to determine the order of reaction under this subsection. Difference between the order and the molecularity. So what are the differences between the order and the molecularity for a particular reaction? We will also learn this. Lastly, we will see some examples from 3.3 to 3.4 as per the NCRT textbook in the chapter Chemical Kinetics. And lastly, we will cover some in-text question along with the example marked as 3.3 to 3.4. So let's begin with our first topic, which is the subsection 3.2.3, order of a reaction. In the rate equation, the rate is determined by k times a to the power x b to the power y. This is marked as NCRT equation 3.4 part A. So if you remember, until now in the previous lecture of the chemical kinetics, we have talked about the kinetics of the reaction and what is rate, how you can define the rate equation, or how the rate law can be expressed, right? The rate constant, right, order of a reaction, and unit of rate constant. This all things we have been studied before. Now in the rate equation, which is given by rate is equals to k times a to the power x and b to the power y, x and y is indicating that how sensitive the rate is to the change in the concentration of A and B, because A is the concentration of the reactant A and B is the concentration of the reactant B of the reaction A plus B giving us C plus D, right? So if A and B are the reactants in a reaction whose power in the power X and Y are present, in the rate equation, then you can see or you can determine that how important the value of x and y are to indicate that how sensitive the rate is to change in concentration of A and B. If we change the concentration of the A and B a little more, the rate will going to affect very much. Okay, this also we have seen through a table that if we double a particular concentration of reactant, then the rate is going to affect majorly, and if we double the another concentration of our another reactant, then rate will not going to affect that much. That's how we will determine the this x and y values, right? This we have covered. So as I'm saying that in this given rate equation, k times a to the power x, b time b to the power y, x and y are indicating that how sensitive the rate is to the change in the concentration of A and B. Sum of these exponents, that means x and y, exponents is the synonym for the power. Okay, so x and y are in the power of the A and B concentration. So if you sum these exponents, that is if you write x plus y, it gives the overall order of a reaction. Okay, so x plus y represents the overall order of a reaction. So if you know a reaction and if you know the rate equation for that particular reaction, if you know the rate law for that particular reaction, that means the reactant concentration are in the product form, and also something is present as power of the concentration of those reactants, and if you add those powers, that will determine the overall order of the reaction. So whereas x and y represents the order with respect to the reactants A and B respectively, so x plus y is representing the overall order of the reaction, and x and y individually representing the order with respect to A and B respectively. That means x is representing order with respect to reactant A, y is representing the order with respect to reactant B. The sum of powers of the concentration of reactants in the rate law expression is called the order of that chemical reaction. So this is the proper definition, that if you sum the powers of concentration of reactants, okay, whatever the concentration of reactants are and their power are present in the rate law. So in the rate law expression, the power, the sum of power of concentration of reactant is called the order of that chemical reaction. So order of a reaction can be 0 because the sum of the exponents can be 0, can be 1, 2, 3, and even it can be a fraction. That means order can be a fraction quantity for a chemical reaction. A zero order reaction means that the rate of the reaction is independent of concentration of reactants. So as I said that zero order reaction, zero order, that means the concentration of both the reactants in the chemical reaction is having no power, not even one power, right? They are having zero power. That means the exponents is having the zero sum. So zero order reaction means that rate of reaction is independent of concentration of reactants, right? Because if something is power zero, that means if you write the a to the power x as a to the power 0, that means a to the power 0 becomes 1, right? That means rate will become equals to k, right? That means there is no concentration of the reactants will be present in the case of the zero order reaction. That's why we are saying that in zero order reaction, it means that rate of the reaction is independent. That means it will not going to depend or affect by the concentration of the reactants present in that reaction. Okay, so okay, one thing to mention, I want to mention that this is try to make this session a little interactive, and if you have any doubt in between the lecture, you can ask in the chat box. Okay, so coming back to our slide, let's talk about the unit of rate constant. Okay, the k which we have seen, that rate equals to k times a to the power x b to the power y. The k in that equation is representing the rate constant. Now what is about the unit of rate constant? So for a general reaction given by small a capital A plus small b capital B, giving us small c capital C plus small d capital D, where A and B, capital A and capital B are representing the reactants, capital C and capital D are are representing the products, and small a small b representing their stoichiometric coefficient. That means the quantity or the moles or the amount of the atoms of A and B or C and D which are present in this reaction. For so let's we are supposing a general reaction which is given by this. So for this, the rate can be expressed as k times a to the power x and b to the power y. Generally, x and y are small a and small b respectively. That means generally the a, that means the concentration of the reactant, is having the power of its stoichiometric coefficient which is present in the chemical reaction and a balanced chemical reaction, but it does not happens in every every way, right? There are exceptions where this does not fit. That's why x plus y gives the n which represents the order of the reactions. Okay, so x and y may or may not be equal to the stoichiometric coefficients of the reactants in a chemical balanced chemical equation. But if for a general reaction, if you have a general reaction and you determine the rate law from that, this x and y, whatever the exponents are present on the concentration of the reactants, when you sum them, it will give the value of n, which represents the order of the reaction. So k, that means this k is determined as or is given as rate divided by the concentration of A to the power x multiplied by the concentration of B to the power y. So this is the k representation in terms of rate and the concentration of the reactants, right? We just interchange some terms from left to right hand side or right to left hand side, and we can determine the k value. So from this, k will be this concentration of A and B will go into the denominator of the rate at the left hand side. So that's why we have written this equation. Now if you write like k is equals to rate upon this, so rate is given by the change of the concentration divided by the time, right? That in particular amount of time, what is the change of concentration, that is determining by rate, that is given by rate, right? So you can write the rate as concentration by time because we are talking about unit. So even if we are talking about the change in concentration, that will also take the unit of the concentration, right? So because change in the unit of change in the concentration is equals to the concentration, some amount of concentration, that means the unit is going to be same. So we can write the rate as concentration divided by time. Now multiply by, we have this in the denominator, a to the power x b to the power y, right? That means a and b both are concentration, so we can write 1 upon concentration to the power n, where n is x plus y, right? Why we add the x and y? Because their a and b, that means their bases are same, right? So exponents bases are same, that means both are defined as concentrations. That's why we have written concentration to the power x plus y, and x plus y is n. So this is the representation. We have clarifying here that a is equals to b. We have considered that the concentration of a is equals to the concentration of b. That's why we have added x and y together to get n here. Taking the SI units of concentration, which is given by mole liter inverse. Now, if you talk about the SI unit of concentration, it is given by mole liter inverse. And similarly for time, the SI unit is seconds. And for the units of K for different reaction order, they are listed in the table 3.3, which we will going to see. The units of K for different reaction order. So let's see the table 3.3 marked in the above point, which is for the units of rate constant. So we have given the 3 columns, each column having something. So first column is having the reaction, the second column is having order, and the third column is having the units of rate constant. So reaction is equals to the first reaction is given as 0 order reaction, and the order for this reaction is given as 0. Now the units of rate constant will be mole liter inverse by second multiply by 1 upon mole liter inverse whole to the power 0. Right? Basically, for the 0 order reaction, the units of rate constant will be K is equals to the concentration unit divided by the time unit multiply by 1 upon, in the denominator we have concentration unit to the power 0, because it is a 0 order reaction. The rate is not going to depend on the concentration of any reactant. Right, so that's why we have written the concentration term and its power 0. So this will become 1. Only this you can solve, which is the unit of rate. So the 0 order rate equation, rate reaction have the units of rate constants equals to mole liter inverse second inverse. For the first order reaction, the order is 1, because already given first order reaction. So order is 1. Now the units of the rate constant will be the rate unit, which is mole liter inverse divided by seconds, multiply by the products unit, which is 1 upon the concentration to the power 1, because it is a first order reaction. That means the concentration to the power something, the power is 1, or the sum of the power is 1. That's why we have written the concentration to the power 1 in the denominator. And when you solve this overall thing, it is coming out as equals to second to the power minus 1. The next reaction is second order reaction, whose order is 2, and the units of rate constant in this case is mole liter inverse per second, which is rate equation, multiply by rate unit multiply by 1 upon the concentration unit to the power 2, that is square, because it is a second order reaction. That means the sum of the power of reactants is coming out as 2. Right, now when you solve this, it is equals to mole inverse liter second inverse. So this is the unit of rate constant for the second order reaction. Okay, now let's talk about our next subtopic, which is 3.2.3, that is molecularity of a reaction. Number of reacting species, that means the number of species, atoms, ions, or molecules, anything can be possible. What are the number of reacting species which are taking part in an elementary reaction? Okay, so the reacting species which are present in the elementary reaction, which must collide the simultaneously in order to bring about a chemical reaction, is called molecularity of a reaction. Okay, so this is the definition, or the basic definition for the molecularity of reaction, that it defines the number of reacting species, either atoms, ions, or molecules, which are taking part in the elementary reaction and which must collide simultaneously in order to bring about a chemical reaction, which is called a molecularity of a reaction. Reaction can be unimolecular when one reacting species is involved. For example, the decomposition of ammonium nitrate. Right. So if we have a reaction which is unimolecular, that means it only contains one molecule. So when the one reacting species is involved, the reaction can be unimolecular when one reacting species is involved. Right, in the rate law, only one reacting species is involved, that means the reaction is unimolecular. For example, the decomposition of ammonium nitrate, NH4 NO3. So this is NH4NO2. Okay, ammonium nitrate, NH4NO2. When it dissociate, it is forming N2 plus 2H2O. Biomolecular reactions involved simultaneous collision between the two species. Okay, the two species having the simultaneous collision. This is involving the biomolecular reactions. For example, the dissociation of hydrogen and iodide. So 2Hi, that means hydrogen iodide, giving us hydrogen molecule and iodine molecule. Continuing on this topic, Triamolecular reactions involve the simultaneous collision between three reacting species. As the name says, trimolecular. Trimolecular means three molecules are colliding at the simultaneous time, okay, between the three reacting species. For example, 2NO plus O2 giving us 2NO2. Now, the probability that more than three molecules can collide and react simultaneously is very small in this case. So, we have seen with the help of example also that in the triamolecular reactions, which is involving simultaneous collision between three reacting particles. So, for example, this reaction of 2NO plus O2 giving us 2NO2, and you can see that probability that more than three molecules can collide, but we have only 2 plus 1 3, right? Only we have three reactant molecules which can collide to make the product, but it is the probability that more than three products or three molecules can combine or can collide and react simultaneously, that probability is very, very small. Now let's talk about the elementary reaction. Okay, so they involves a single step. That's why the name says elementary. That means in a single step they will going to complete. So NH4NO2 converting to N2 plus 2H2O. Now 2HI giving us H2 plus I2. 2NO plus O2 giving us 2NO2. Okay, so these are the examples of elementary reaction. Only single step are involving in them. Then we talk about the complex reaction where more than one step is possible. So they involves the multiple elementary steps like 2H2O2, that means two hydrogen peroxide molecules in the presence of alkaline medium and I negative. It is converting to the two molecules of water and giving us oxygen molecule. So they are happening in the multiple elementary steps. So what is the first step? Firstly, the H2O2 reacts with the I negative ion in the RDS and the formation of H2 and IO negative is forming, right? This is the first step of combination of this I negative with the reactant, which is H2O2, and it is giving us H2O molecule and IO negative. Now what we have remained with? One molecule of H2O2 and one molecule of water, and one molecule of O2 we also want to get, right? So like a second step involves the reaction of the second H2O2 molecule with IO negative just prepared, and they will give us H2O, one I negative and one oxygen molecule. So these are the elementary steps to getting to get the final major products in the complex reactions. Now let's talk about the determining of order of the reaction, that how can you tell the order of the reaction and what is the process. So rate law for any reaction cannot be predicted by merely looking at the balanced chemical equation, that is theoretically, but must be determined experimentally. So what we are saying that for any reaction, the rate law cannot be predicted by merely looking at the reaction or by merely looking at balanced chemical equation. We cannot write the rate law. That is, we cannot theoretically tell the rate law, but it need to check the rate of the reaction experimentally, because the reaction rate is determined, or rate law for the reaction is determined experimentally rather than theoretically. Now for the elementary reactions, which are the type of the reaction which happens in one step. So for these type of reactions, the molecularity is equals to the order of the reaction. And for the complex reaction, the order is given by slowest step, and molecularity of slowest step is same as the order of the overall reaction. Okay, so order is given by the slowest step for the complex reaction, because it doesn't happen in the single step, it happens in the multiple steps. So order is determined by the step which is slowest, and the molecularity of that slowest step is same as the order of the overall reaction. Determining the order of the reaction, and we have this equation reaction, which is KClO3 plus 6FeSO4 plus 3H2SO4 converting to KCl plus 3Fe2SO4 whole thrice plus 3H2O. So this reaction, which apparently seems to be of 10th order due to the presence of this much amount of reactant here, but it is a second order reaction. It is not 10th order but a second order reaction. The overall rate of the reaction is controlled by slowest step in a reaction called rate determining step. Now for the overall rate of the reaction that we can control or that we can determine by slowest step in a reaction, which is called as that slowest step is also has name, that it is called as rate determining step. For example, the chances to win the relay race competition by a team which is depend upon the slowest person in the team, right? So for example, we have a chance to win the relay race competition by that team which depends upon the slowest person in the team, right? So this is like that rate determining step, which is a slowest step in a reaction, the overall rate of the reaction is controlled by that slowest step. Now let's see that what is the difference between the order and the molecularity of the reaction. So we can represent this, or we can tell that with the help of this given table, where the order of the reaction is present in the one column and the molecularity is defined in the another column. The order of reaction is saying that it represents the sum of exponents of concentration terms in the rate of equation. Okay, so whenever we are having the reaction or rate law, the order of reaction is represents the sum of exponents of concentration terms. Whatever the concentration term has their power, when you have to add them, then you can get the order of the reaction in the rate equation. Okay, so that is the order of the reaction. Now for the molecularity represents the number of reactant particles. That means how many reactant particles want to or will be going to collide, right? So molecularity is representing the number of reactant particles which are involved in the elementary reaction. Now order of reaction can be determined experimentally. We can determine the order of reaction experimentally, but the molecularity can only be determined theoretically. Okay, we can't use here any experimental data for the determination of molecularity. Order of a reaction can be 0, fractional, or a whole number. Okay, so order of reaction can be 0, can be fractional, can be whole number. Meanwhile, the molecularity uh, can only be a whole number. So molecularity can only be a whole number, not satisfying with fractional or zero number. But order of reaction can have zero and fractional value along with the whole number value. Order is applicable to elementary as well as all the complex reactions. So what we are saying that in the order of the reaction column, this is this is very basic by the way, that order is applicable to the elementary as well as the customers, uh, because we are going to get that from our complex reactions, right? So that's why and in the molecularity is application only for the elementary reactions which happens on the single step. For example, the reaction molecularity has no meaning. Okay, the reaction molecularity has no meaning, only the molecularity has meaning, which is applicable only for the elementary reactions. Okay, now let's see an example which is marked as 3.3 in our NCERT textbook. Example is saying that calculate the overall order of a reaction which has the rate expression as A and B. So rate is given by K times A to the power half B times 3 by 2. B is rate is equals to K times A to the power 3 by 2. B is B to the power minus 1. Right? So you have to calculate the overall order of a reaction which has uh, the rate expression of which kind. So you got some time, try to solve this, and then we will see that what is the correct answer. Okay, so let's see. So for this given question, let's see how you can solve this and how can you get the overall order of the reaction. So the rate is given as K times A to the power X, B to the power Y in general form, right? So we can match this with the two A and B. So order will be X plus Y is equals to N, right? Order. So here in the first case, the order will be half plus 3 by 2, right? Which is 4 by 2, which is 2. So order is 2, that is second order. Similarly, for the B, which have the order as the sum of the exponents of the concentration present in the rate law. So rate law is given in the B as rate is equals to K times A to the power 3 by 2, B to the power minus 1. So order will be 3 by 2 plus minus 1, which is basically 1 by 2, right? So 1 by 2. So in the B, the order is coming out as 1 by 2, that is half order, right? So for the A, the overall order of the reaction is 2, that is second order. And for the B rate law, the overall order of a reaction is given as half order. Now let's see our next example, which is marked as 3.4 in our NCERT textbook. It is saying that identify the reaction order from which of the following rate constant. Okay, so identify the reaction order from which of the following rate constant. So we have given some rate constant. The K is 2.3 times 10 to the power minus 5 liter mole inverse second inverse, and K is equals to 3 times 10 to the power minus 4 second inverse, right? So in the question it was asked that you have to identify the reaction order from each of the following rate constant, just given as 1 and 2. What does that mean? That is what you are explaining is that uh, that for the first and the second, that is the for the K value which is given differently, the reaction order you have to tell for these two rate constant values. So you have given some time, try to solve this, and then we will see that which is the correct answer. Okay, let's see. So for this given question, the unit of the second order rate constant is liter mole inverse second inverse. Therefore, the K is equals to 2.3 times 10 to the power minus 5 liter mole inverse second inverse represents a second order reaction. So as the question asks that you have to identify the reaction order from the given rate constant value. So we have given the rate constant values along with their units, and previously we have studied about the unit of rate constant, that how can you determine the units for the rate constant for the different order reactions, right? Now the unit of the second order reaction rate constant is liter mole inverse second inverse, and it is same as present in the first part of our question, the rate constant value or unit. So both units are matching, therefore we can say that K is equals to 2.3 times 10 to the power minus 5. Later mole inverse second inverse represents a second order reaction. Similarly, for the second K value, the unit of a first order rate constant is. So unit, if you observe the unit of first order rate constant, it is given by second inverse, and it is same unit which is present in our second uh, choice of the rate constant. That's why if the both are same, we can say that therefore K is equals to 3 times 10 to the power 4 or 10 to the power minus 4 second inverse, which is representing a first order reaction. Now let's see our in-text question as per our NCERT textbook, which is marked as question number 3.3. The question is saying that for a reaction A plus B giving us products, the rate law is given by R is equals to K times A concentration to the power half, B concentration to the power 2. This is the given rate law in the question already, right? So what is the order of the reaction? You have to tell the order of the reaction by just looking at this rate law. So you have some time, try to solve this, and then we will see that what is the correct answer. Okay, let's see. So for this given question, the rate law is provided as, in the question we have given the rate law for the reaction A plus B giving us product. So the rate law is provided as R is equals to K times A to the power half, B to the power 2, right? Where A and B are the reactants in the reaction. K is a rate constant, R is representing the rate. So in the rate law, the power of A is half. Similarly, the power of B is 2. So the overall order of the reaction is sum of power of concentration of reactants. Okay, you have to sum the powers of concentration of the reactants. That means we have this reactants A and B. Their concentration power is half and 2 respectively for A and B. You have to sum them to get the order of the reaction. Therefore, we calculate the order is equals to the power of the A plus the power of the B. So power of A is half, so half plus power of B is given as 2. So half plus 2. Now when you solve this fraction, you just have to take the LCM. So here comes the 4, 2 times 2 is 4. 4 plus 1 is 5, so there the order therefore will be 1 by 2 plus 4 by 2, which is 5 by 2. Thus, the order of the reaction is 5 by 2. As we have seen that, as I mentioned, that order can be 0, 1, 2, 3, and even can be a fraction. So here you can see that order of this reaction A plus B giving us product on the basis of the given information of the rate law. We determine the order for this reaction as 5 by 2, which is a fraction. Okay, which is a fraction. So order can be a fraction too. Okay, so let's see our next question, which is again a in-text question marked as 3.4 in our chapter Chemical Kinetics in the NCERT textbook. The question is saying that conversion of molecules X 2y follows second order kinetics? If the concentration of X is increased to 3 times, how will it going to affect the rate of formation of Y? So when you convert the molecule of X, or when you convert the molecule X to Y, it will follow second order kinetics. Okay, so we have already tell the second order rate of the reaction, that it will be going to be second order. Now if the concentration of the X is increased to the 3 times, how will it is going to affect the rate of formation of Y? Okay, so that was the question. You got some time, try to solve this, and then we will see that how can you answer that, and how and what will be the correct answer for this question. Okay, let's see. So for this given question, the rate of a reaction that follows second order kinetics can be expressed as, so in the question we have asked that if you are converting the molecules X to the Y, it is following the second order kinetics. Now if the concentration of X is increased to 3 times, how the rate of formation of Y will going to affect? So as you know that rate of a reaction which follows the second order kinetics can be expressed as rate is equals to k to the power kx to the power 2. X is representing the reactant of the reaction. 2 is representing that the conversion of X to Y is a second order kinetics. So this is the rate expression or rate law. Rate is equals to k times 10x to the power 2. Now k here is representing the rate constant, and x is representing the concentration of the reactant X present in the reaction. Let the initial concentration of X be small x. Okay. Therefore, the initial rate of reaction can be written as R1, initial rate of reaction R1 is equals to K times X to the power 2. And if we have given the X concentration, if we have taken the X concentration as equals to small x, you can write it as R1 is equals to Kx square. Now, according to the question given, the concentration of the X is increased to 3 times of its original value. As it's mentioned, that concentration of X is increased to 3 times, how the rate of formation of Y is going to affect. So, if the concentration of X is increasing to 3 times to its original value, the X concentration will become 3x, because X concentration, initial concentration of X we have taken as X. So after the increase of concentration to 3 times, the X concentration will become equals to 3x. Now, the substituting the new concentration into the rate law, which is this x equals to 3x, when you substitute it into the rate law, we get the new rate as R2. So R2 is given by k times 3x to the power whole square. Right, 3 times the concentration increase, so 3 times x whole square, which is equals to k 3x whole square, right? So R2 will become k times 9x square, because 3 square will be 9, x square will be x square, so we can write it as 9k x square. Now to find out that how the new rate, which is R2, is comparing to the initial rate R1, we can set up the ratio following, which is R2 by R1. This was the question, that how will the after the change of X in concentration to 3 times increase, how it will going to affect the rate of formation of Y, right? This was the question. So if you want to compare the rate of the initial thing and the final thing, then you can write as R2 by R1 is equals to 9kx square upon kx square, right? Now x and x are same, k and k, which is rate constant, they are also same, so they will cancel out. The remaining thing will be 9, right? So we find that, that R2 is equals to 9 times of R1. R2 is the rate of the reaction after the increase of the concentration of X to the 3 times. So final rate is equals to the 9 times of the initial rate, which is R1. The rate of formation of Y will increase by a factor of 9 when you increase the concentration of X, which is reactant, to 3 times its original value. And Y is a product here, by the way. So if you are increasing the concentration of the reactant X to 3 times, the rate of formation of Y is increasing by 9 factor. Okay. So the rate of formation of Y will increase 9 times. You can say that if you are increasing the X as 3 times, the Y formation, the rate of formation of Y, that is product, will increase by 9 times. Okay, so that's why this is how you can compare the two rates, and according to the given information, this is how you can get the information about the two rates after the increase of the concentration of reactants, and you can get the information about the affection of this increase in the concentration of reactant to the formation of Y, which is product. Okay, so how the product is going to affect, that's how you can see. Okay. Okay, thank you so much for joining this chemistry session. This is all for today's chemistry session.